Hello there and welcome to my channel, Finn Does Chemistry. My name is Finn and I have a red cabbage. Actually, that's a lie, I have half a red cabbage because my mom wants to use the rest to make dinner. Either way, red cabbage has some really interesting chemical properties. So in this video, I'm going to show you an experiment using red cabbage that you can do at home. That's water, that is. What we're going to do today is turn our red cabbage into a pH indicator, which means we can use it to test whether a substance is acidic or basic. So what does that mean? Well, first let's start by looking at water. Most water molecules go around in this form, but some will always spontaneously dissociate at room temperature into this form, where it exists as a H+ proton and an OH- hydroxide ion. At 25 degrees Celsius, the equilibrium constant Kw for this dissociation reaction is 1 × 10⁻⁴, which means at any one time, 1 in 100 trillion water molecules exists in the dissociated form here. To convert our dissociation constant into a number that's a bit easier for us to handle, let's use pKw instead of Kw. And you can transfer between the two using this equation. So plugging in this value of Kw, we get this calculation which gives us a pKw of 14 at 25 degrees Celsius. Now similarly, from here on in, we're going to use pH and pOH rather than the concentrations of protons and hydroxide ions respectively, just because the numbers are way easier to work with. So what are pH and pOH in water? Well, pKw is a constant, which means no matter what, at 25 degrees, pKw will always be equal to 14. What we also know is, looking at this equation up here, one molecule of water will always associate into one proton and one hydroxide ion, which means that we'll always have an equal amount of both. So we can say that pH is equal to pOH in this system. So with some simple maths, we can work out that in water, pH and pOH are both equal to 7. So that was water. Now let's think about an acidic substance. An acid, by the Bronsted-Lowry definition, is a proton donor, and the better of a proton donor a molecule is, the better an acid it is, or the stronger an acid it is. So if we think about an acid in water, the acid can actually give up its proton to solution, therefore increasing the concentration of protons in solution. So it's important to realise that the concentration of protons in solution and pH are actually inversely proportional. So the higher the concentration of protons, the lower the pH. So this is why, on a pH scale like this, which you might be familiar with, acids are going to have a pH lower than 7. So this whole region, all of this, belongs to acids. Bases, on the other hand, by the Bronsted-Lowry definition again, are proton acceptors. So these are mopping up all of the protons that are flying around in solution, resulting in pOH being greater than pH. So once again, we're decreasing the concentration of protons, which means we're increasing the pH, which means this region along here belongs to our bases. So even if you haven't understood any of the maths up to this point, all you actually need to know, pH greater than 7 means we have a lower concentration of protons and a higher pH. That means it's a base. And vice versa, if we have a higher concentration of protons, we are decreasing the pH and we have an acid. So just as an example, a weak base could have a pH of say 9, but a stronger base, which means a molecule with a greater affinity for protons and mops up more of them out of the aqueous environment that it's in, could have a pH of up to 14, or higher in some cases, but we're not going to deal with anything outside of the 0 to 14 pH range today. I need more light. Gorgeous. It's common misconception time! If you've learned anything about pH in the past, you've probably learned that a neutral substance will have a pH of 7. And that's kind of true, but it's kind of not. So water is a neutral substance, and at 25 degrees, water does have a pH of 7. However, the definition of pH is not that the pH What? The definition of neutral is not that the pH is 7. The definition of neutral is that pH equals pOH. So if you recall that pH plus pOH equals your pKw value, pKw is 14 at 25 degrees Celsius, which means that our pH and pOH both equal 7. However, when we increase the temperature in our system, the water molecules are more likely to dissociate because they have more energy, which means that the dissociation constant gets higher at higher temperatures and the pKw value gets lower. So at 60 degrees, pKw is actually closer to 13, which means in order for our substance to be neutral, for pH to equal pOH, our water is actually going to have a pH of 6.5. So that's why it's only valid to say that neutral substances have a pH of 7 at 25 degrees Celsius. Common misconception, busted. That was terrible, I'm never doing that again. What is that? What a treat for you guys. Hi, baby. She just likes to sit there. Oh. How long's that been wonky? You guys didn't tell me that. Rude. Thank you guys for sitting through all that maths. I know it was a lot, but now it's time for the experiment. We're moving outside because my mum doesn't want me doing chemistry inside the house. If you're following along at home, all you need is a red cabbage, some water and a way to heat it up, a sieve or filter of some kind, a jug, some glasses, the kitchen kind, not the eye kind. The only other thing we're going to need is some acids and bases to test. This is going to work best with a range of strong acids to strong bases. As a general rule, food items are going to tend to be acidic, so that's your lemon juice, your vinegar, milk even. If it has that kind of sharp taste to it, then it's likely to be a stronger acid. And bases tend to be your household cleaning products. There's a cat here. Say hi. Oh! God, it's just started raining, so sorry mum. I'm doing this inside after all. Thank you. Okay, we're inside now. I hear you asking, Finn, why aren't you in the middle of the frame? We've got a lab partner today. She looks like she might kill me any moment actually, so I'm gonna stop stroking her. Let me show you what I've got for us to work with. First off, orange and mango flavoured sparkling spring water. Now we're assuming this is going to be acidic because of the carbon dioxide that's dissolved in the water. We've got a classic lemon juice situation. This one may or may not work properly, you'll see why later in the video, but just in case it doesn't, I've got another fairly strong acid, this distilled vinegar. As for our bases, the first thing is going to be some bicarb of soda, and actually the reason this is base is in the name bicarbonate. Carbonate groups are basic, so for this to work we do need it to be a liquid, so we're just going to dissolve that in some water a bit later. Next we have this glass and mirror cleaner. Pretty much any household cleaner will work. Most of them are ammonia based, which is our base in this instance. And last but not least, I have us some drain cleaner, and I'm not actually sure what's it's made out of. Caustic soda, very basic. So yeah, I'm guessing this is going to be our strongest base of the lot. So this is our lineup. Especially when you're handling like quite intense cleaning agents, I'm going to recommend that you use gloves and actually goggles. Just in case of any splashes. You don't want any of this stuff getting in your eyes. That's nasty, nasty, nasty stuff. Oh! Ah! You... Oh, her claw is stuck in my trousers. For what reason? For what reason? I've just been viciously attacked. What do you have to say for yourself? And that's everything we need. So now we're going to get on with making the actual indicator solution. So this is actually super simple. First thing we want to do is just chop up our red cabbage. The smaller the better, really, but I wouldn't stick it in a blend. I'm sorry for pointing that at you, I apologise. Nice small chunks are going to be best, but I wouldn't be in a rush to put it in the blender or anything, because you're going to have to separate out all of the pulp later on. And if you just blend it, turn it into red cabbage soup, that's going to make it a bit difficult. Kids, if there are kids watching this, get your parents to do this, yeah? Oh, she's back for more. It's everywhere! So I'm going to show you guys something real quick. So when you have a piece like this versus a piece like this, so this one kind of has all of the white in the middle of it, like it's one of those really thick leaves at the centre of the red cabbage, and this is one of the outer leaves, it's much thinner. These thinner leaves are going to be the ones that give you the best results. So if you have a choice between using kind of the outer leaves of the red cabbage versus the like centre of it, use the outer leaves. I'm just going to use both because I have both, so why not? Alright, so I've got what could be considered way too much red cabbage actually, but we move. Now all we need to do is just add some hot water. This is fresh out of the kettle. There we go, and you can see we're already getting that nice blue colour. By the way, we don't even need to turn the heat on with this. You can already see that the colour is leaching out into the water. That's exactly what we want, so we're actually just going to leave that to soak for a while. So I've left that to soak for about 15 minutes. So I feel like now's a good time to tell you about anthocyanins. Anthocyanins are the molecules in red cabbage that actually allow it to behave as a pH indicator, because depending on the pH of the solution that it's in, it can change colour. So behind me, we have an anthocyanin at pH 0, but the more protons are removed from that structure, the more the colour changes. So this reaction scheme shows how anthocyanins behave at different pH levels. Very low concentrations of OH-, so in an acidic solution with very low pH, it exists in its cationic form with a positive charge. If you abstract a proton with a base, for example a hydroxide ion, you get this purple species. Now, two things can happen. Either another proton is abstracted by even more base to make this blue species, or a hydration reaction can occur, creating this colourless compound, which in turn can undergo a ring opening reaction and turn yellow in the process. All of these steps are reversible, with all of the equilibrium constants being dependent on the concentrations of H+ or OH- in solution, which is just a fancy way of saying that at very high concentrations of H+, meaning at low pH, we mostly get the red form, and at very high concentrations of OH-, meaning a high pH, we get mostly the yellow form, and in between those two extremes there's a sliding scale of shades of red, pink, purple, blue and green. So it's been about 15-20 minutes. Looks good. Alright then, so now we've got our solution. We're just going to strain it into the jug, see how it looks. There we go. Oh my gosh. There is way more here than I need. So what I'm actually going to do is I'm going to dilute this down a little bit more. I'm going to go put some more water in it, and then hopefully we'll be able to see the colour a bit clearer. That's really nice actually. I'm really pleased with how that turned out. So look here, you can see we've got that gorgeous kind of bluey purple colour. That's exactly what we want. If yours looks a bit more blue and a bit less purple than that, don't worry, it probably just means that your water source has more ions in it, it's a bit more alkaline. And here we are with all of our glasses set up and ready. Sorry about these ones, by the way. I know they're not the easiest to actually see into. Subscribe and I'll buy conical flasks. Got a Diet Coke as well. That's not for the experiment, that's just for refreshment. So let's pop everything in our jars. Glasses. So unfortunately with the lemon juice, because it's not colourless, it might be a bit difficult to see exactly what's going on with the pH, but we'll give it a go anyway. Also, there's the cat. She's just chilling. The sodium bicarb is obviously a bit different because it's a solid in here, it's a powder. So I'm going to show you what we're going to do about that. So right now I've just gone and filled that with water. And now we're just going to try and dissolve it until no more dissolves. I reckon that's probably enough. Now we're getting to the bit that you might want gloves for. I can't be putting my face this close to the vinegar. Ah! Oh, it's an interesting, why is it that colour? Oh, wow. I thought it was going to be clear. Oh god. It's childproof. Ugh. But I'm not a child, so I opened it. Oh, oops. Alright, amazing. So now that we've got our lineup, I guess all that's left is to add our indicator. So, no real surprise there. We haven't really had a colour change at all. Yes. Definitely more blue. Here we go. It's much, much clearer if we have light shining from the back of it. It's kind of just turned a weird muddy colour. Down with the cleaning spray. We don't need it. We don't need this. Whoa! It's phase separated. Oh, but it's turning yellow. It kind of is. Oh, that's so funky. Look, if I compare that to the water, it's gone from like purple to... That's a really nice colour actually. Oh, I want to drink it. If I pop it next to this one, you can see how it's definitely more orangey, and that's probably because of the yellow in the lemon juice. I feel like because that's coloured, we should just discard that because we don't know how much the colour is affecting the colour of the indicator, if that makes sense. Yeah! Oh, that's nice! Okay, yeah, again, if you line them up so that light is shining through the back of them, you can definitely tell the difference there. So cool. And so here they all are. And there you have it. We've got all of these sick colours. I'm a bit sad that we didn't get a kind of green in-betweeny one with that cleaning fluid. I might actually try and get a green one just by using really, really dilute drain cleaner. Might as well try, right? Do the tiniest little whoop. Now I'm gonna go and fill that with some water. And we're gonna dilute it even further with our indicator mixture. Yes! Oh yes! That is so cool. It's still really slowly changing from green to yellow. Still not really green, but I'll take it. It's actually stopped raining now, so we can do one of the experiments we were going to do a bit earlier. All you're going to need for this is your bicarbonate of soda and your vinegar, and you might want to put a little bit of washing up liquid in there just for fun. I'll show you how we're going to do it, so don't worry. First thing is, we're actually just going to make our bicarbonate solution again, so this is just water. Bit of that in there. Oh my god, that's way too much. And we're going to add more of our indicator. Nice. And finally, just for fun, that means we're going to get some nice cool bubbles. This reaction is going to produce some carbon dioxide gas, so I'm really hoping that adding that washing up liquid will make it all like froth up like crazy, and it's going to look really cool. Bless you. So now I've got my bicarb solution, and I've got my vinegar, and we're going to take this outside. Okay, there's our sodium bicarb. Let's add the vinegar and see what it do. That wasn't as good as I thought it would be, but still, it's pink now. Well, that was maybe a little bit anticlimactic. We got the colour change, but I was really hoping that it would like foam over and look really cool. But yeah, really, it wasn't the right shape glassware, first off, and secondly, it's probably not concentrated enough for a really vigorous reaction. But we still got the colour change, which I'm pleased with. It's actually started raining again, so I'm gonna run back inside, but thank you for watching. I'd love it if you left a comment down below, told me if you liked the video. Give me ideas for future videos if you'd like. I feel I need like an outro or something. Keep it chemical. Oh, that's awful, I can't say that. Well, until next time, keep it chemical, I guess. See ya.